All right, everybody, welcome back. So in this video, we're going to be talking about the heat treatments of steel. And so basically, the purpose of heat treating is to change the physical properties or the mechanical properties of steel. So this is to do things like increase the hardness and strength, increase ductility, or I should say decrease brittleness, things of that nature. So basically, are we going to harden steel, or are we going to soften it? Things like that. Hardening it is going to make it harder to work with, bending it, things of that nature. So when we need to shape it, we tend to need to soften it. So when we think about heating steel up, heat treating it, we can do it in a couple different ways. We can do it by a flame. So if we look at this image down here, you can barely see that there's a torch, but there is a flame coming out of it, and here's a piece of steel that's being heated up. You can kind of see that it's already starting to get that nice orange glow. And then up top here, this is a heating oven for heating up metals. And so here's a nice big chunk of steel right here that's just about ready to get taken out and formed into whatever shape the user needs. Or we can use induction coils, but that one's a little bit harder to do for industrial applications. So we're just going to be talking about using an oven or using a flame. And so there are a couple different things that people can use to judge the temperature other than using something like a thermometer, and that is using a color scale. So there are a couple differences with these color scales that I want to point out first and foremost. So this image down here is more for tempering steel, and I'll get to tempering in a little bit in a later slide that's coming up. But this is when we're just heating up steel gradually. So this is not to a point where steel is going to be glowing. This is just heating it up just a little bit to where you can tell the temperature by the color of steel. And so steel will change color based on how hot it's getting. And this image right here has two different scales. The one on the right is for tempering. You can see a lot of these colors in this image. And this column right here is for when we're, heating it up to that critical temperature to where steel is about to become a liquid. And so this is, again, we can use the color of the steel to determine a general idea, an approximation of how hot it is without having a means to get an exact temperature, like using maybe something like an infrared thermometer, a laser thermometer, something like that. We can use the color to judge how hot this material is. And so when we start talking about heat treatments, I want to tell you that there are 4 different heat treatments. 4 of them. And we're going to talk about all 4. And we're even going to talk about a 5th that a lot of people confuse for being an actual heat treatment. So the first one is annealing. So whenever we're annealing something, we are taking it at whatever point that it's been hardened or it's been softened, and we're going to soften it to basically it's max. So we're going to soften it as much as we can. So once we anneal steel, it pretty much isn't going to get any softer than how soft it's going to be after the process of annealing. So this is when we heat it up to like that bright yellow glowing temperature. A lot of people say, the transformation temperature, and I'm going to talk about that in a little bit, but depending on the carbon content of steel, the transformation temperature can range. So we just kind of say, heat the steel up to its transformation temperature, and then we slowly cool it down. So this isn't, dunking it in water. This isn't kind of letting it cool by itself. When we're annealing something, we get it super hot. We keep it at that temperature for a little bit, and then we control how slow it cools down. So we keep applying heat to it but over time we're going to reduce that heat. We're going to turn it down so that way we're still hitting it with heat, but we're reducing it little by little by little over time to a point where it can cool off to say room temperature, and we can pick it up with our bare hands. And after that time of heating it up and slowly cooling it down, that steel is going to be soft. Now, it's not going to be like Play-Doh. It's not going to be like, rubber. It's still going to be steel, but it's going to be easier to hammer it into shape, to bend it using hand tools, maybe a vise. It's going to be easily manipulated than before it was before the annealing process. And then here are a couple definitions straight out of standard code books that you can go ahead and read on your own. And so, stress relieving. A lot of people will think of tempering or even annealing as a form of stress relieving. But it's not a true form of heat treatment. When we talk about stress relieving, we're heating something up just to remove some of the brittleness. So one thing that you should be learning in your welding classes, particularly metallurgy, is that when you weld something, the rest of the metal is going to pull heat away from the area that's been welded. The area that's being welded is being hit with a couple thousand up to 3,000-4,000 degree temperatures because of the weld, and the material and the rest of the project is cold, and so that heat gets distributed throughout the entire piece. And so what happens is these areas right here that are welded, they can become brittle. The forces of expansion and contraction can cause cracks to form either alongside the weld or within the weld. And so you take a look at these things that look like cotton sheets or like these blankets. That's exactly what they are. They're blankets. They are heating blankets, and these coils are actually like heating coils. These are wrapped around areas that have been welded in order to heat it up. Now, you're definitely not going to heat these up to a glowing, red hot or a glowing yellow. It's just going to heat it up just a little bit so that way it reduces the stress around the weld to minimize the risk of cracking. So when people often say tempering is a form of stress relieving or annealing is a form of stress relieving, they can be used to reduce the stress around the weld, but if it's only for the purpose of stress relieving, then it's not a heat treatment. So I just want to go ahead and get that out of the way. So remember, backtracking, annealing is heating up the metal to its transformation temperature and then slowly cooling it down. This is technically not a heat treatment. This is something else that is good to know for welding, but it's not a heat treatment. And then quenching or hardening. This is a form of heat treatment. This is when we take steel and we heat it up to its transformation temperature. We heat it up to an orange or yellow, and then we cool it down rapidly. Now in the image, we have someone here dipping this red hot steel into a bucket of water. You don't have to just use water. You can use something else like a bucket of sand. You can use oil. Some people actually use a stream of cold air to quench the steel. There are many different ways to quench steel in order to harden it. But basically, as long as you're able to cool it down rapidly, and we're talking a matter of seconds. If you can take red hot steel and cool it down in a matter of seconds, basically that's hardening steel. So you can call it quenching, you can call it hardening, either or, it works. This is the second heat treatment. And then there's tempering. So tempering is similar to annealing. You're heating up metal a little bit, and then you're allowing it to cool off in order to slightly soften the metal. But this is done to metal that's already been hardened, it's already been quenched, and you're only softening it so that way it can be used in a setting where maybe it's going to be taking really fast impact. So like shock, it's going to be taking a lot of weight or a lot of force suddenly. So in this image, there are a couple knives. And so you can see on the back of the knife, so along the spine of the knife, you can see this color change. You can see a little bit of blue in there. So these are regions that have been tempered. So if we look back to these scales, okay, so we can see that the blue, the steel's been heated up to like, close to like 600 degrees. This is taking something that has been hardened and we're just softening a little bit. So that way, if we were to subject that metal to really quick impacts or, sharp blows, it's not going to break. It's not going to snap because it's not brittle anymore. When we temper material, we're taking something that's already been hardened, we're heating it up, but not to the transformation temperature. We're just heating it up a little bit. We're looking for those color changes, and then we're going to allow it to cool by itself in room temperature air. And then there's normalizing. So here we have induction coils. This is the only example I'm going to give you because it's not really widely used in welding and fabricating for just because it's very limited in its application. The pieces have to be small enough to fit through these coils, and it's not very practical in a lot of shops. So that's why we'll use ovens and torches instead of these. So normalizing is when we take steel that has been hardened, it's been annealed, tempered, whatever. It can have any type of heat treatment applied to it already. We're basically doing what the name says. We're kind of returning it back to its normal state. So what we're going to do is we're going to heat it up to the transformation temperature, or basically when it starts to glow, and then we're going to let it cool down by itself in room temperature air. So like I said, this is basically bringing the steel back to its original state. Before it was hardened, before it was tempered, before it was annealed, we're bringing it back to its original state. And so here's just a little bit of information about the critical temperature, or what we'll say is the transformation temperature. So basically there are two temperatures. There is the lower transformation temperature, and then there's the upper transformation temperature. Now, generally, the lower transformation temperature is around 1300 degrees Fahrenheit. Okay, so right here. Some people will say it's 1333. This right out of a standard classification code book says it's 1335. It's around that temperature range. And then the upper transformation temperature, it depends on the type of steel, really. And so this chart is the iron carbon phase diagram. Some people have also referred to it as the iron equilibrium chart. And you'll learn more about this in metallurgy classes. But basically, you can use this chart, as confusing as it looks, you can use it to kind of troubleshoot or assess what state of hardness or brittleness or anything like that your steel happens to be in. And it's all based on the carbon content of the steel, the temperature of which it's been exposed to, and how long it's been subjected to that temperature. So this is where knowing the carbon content of your steel is super important. So we have 1%, 2%, all the way up to 6.7. So this is kind of like a brief chart. The actual more comprehensive chart goes up to, I believe, 9%, maybe 8%. So this is kind of just a basic version of the chart. And so if we were to take something like, say, I don't know, 1020, let's just say like 1020 steel. So we'd be right here. Now, if we keep going up, keep going up, keep going up, all the way up. Actually, no, sorry, right here. Lower transformation temperature. Okay, so right here is 1000 degrees Fahrenheit. Here's 1500. So about right here is going to be 1335. So this is the lower transformation temperature. And one thing that you'll learn in your metallurgy classes is that this range right here is the typical range of steel when it becomes austenitic. That is when steel becomes non-magnetic because it's so hot. Right here is the lower transformation temperature. Right here is the upper transformation temperature. So that looks like maybe 2150-ish. Probably 2150-ish. I don't remember the number right off the top of my head, but lower transformation temperature, upper transformation temperature. We have carbon content down here, temperature in Fahrenheit, temperature in Celsius, and one thing that's not calculated on here is the time, but the more comprehensive iron carbon phase diagram will have something on there to include time, so where you can see exactly what grain structure your steel happens to have depending on the carbon content and what temperature it's been exposed to for however long amount of time. This is important because when we talk about heat treatments, if we go back to quenching and hardening, when we quench steel, it hardens it a lot. It increases the hardness and increases strength a little bit. But what happens when those go up, the ductility and the tensile strength tend to go down. Okay, so when something is brittle, it's not very ductile. So when hardness increases, so does brittleness. This is why we temper steel. We temper steel so that way we can get a good balance of ductility and hardness. I'm sure if you've ever watched shows like, say, Forged in Fire, when they're testing the blades on like the strength test, and you see some of the blades, you know, crack, break into itty bitty pieces, you know, they snap. It's because they were too hard and they weren't correctly tempered. All right, so that's the reason why we temper steel. Okay, so, you know, for example, these knives could be like chopping knives or survival knives. They're something that are going to be used to hit something really hard, really fast. And while the cutting edge needs to be hard, the spine should be a little soft in order to absorb the impact, absorb the shock, and keep the knife from essentially, you know, snapping into multiple little small pieces. Okay, so again, talking about strength, hardness, brittleness, ductility, and toughness. So what do all these basically mean? If we talk about strength, strength is the ability to resist deformation. So strength is basically, can the material resist bending? So we have a couple different pieces of metal. These were machined and put into a special machine that basically pulls them apart to test strength. Now, what it does is it pulls on both ends of this little metal piece until it eventually rips apart. And so if we take a look at the image on the right, you'll see that it's very, very clean, very sharp, separation. It looks like there was no stretching whatsoever. So this is when the piece is brittle. So there was absolutely no bending, no stretching. So this is something that has been hardened. And so while it's a little strong and it's very hard, it's brittle and it's not ductile whatsoever. Whereas the specimen on the left, you can see that it was stretched out a little bit. So it's stronger, it's more ductile, but it wasn't as hard. And if we talk about hardness, hardness is basically the resistance or the ability to resist penetration. So this is if you were to try to scratch metal, if you were to try to use a chisel and hammer into the surface of the material, or in this image, you're trying to use a center punch and a hammer to create a divot on the surface of the material. So when you harden a piece of steel, you're basically making it resistant to something piercing the surface. And in brittleness, we had just talked about this a little bit. It's when the metal eventually breaks, does it take a long time for the metal to break, or does it happen at the snap of your finger? Is it, very rough, jagged? When you look inside, is the grain structure fine or is it coarse? If it's fine, it could still be brittle, but it's not as brittle. If the grain structure is very coarse and open, then the brittleness was a little bit higher. And so like I was talking about forged in fire, we got a blade right here that was not tempered properly, and when it was used, it just, it cracked. And then ductility. So ductility is the ability of steel to be bent. And when we talk about this, we have an image of Superman, bending this rebar. It's how well it can be shaped, how well it can be formed or drawn out. So ductility is basically, you can think of it as like the stretchiness of steel. And then the toughness is basically how well it holds up to sudden shock or sudden applied force. So these examples here are machined metal pieces that just came out of a Charpy V-notch test. And so there's a little notch that's made into them. And basically this hammer is suspended up in the air, and it's released, and it comes down and it hits the steel. It records how much force was taken to snap this piece in two. And so toughness is basically, can something hit the steel, and will the steel be able to hold its shape? And then how much force does it take to bend the steel out of shape? Oops, sorry. And then so heat treating can be a tedious process. It's not something that someone gets perfect the first time. It takes practice. It takes experience. It's basically just the heating and cooling of metal, and at what temperature you're doing this at. So remember, as hardness increases, so does the brittleness. As hardness goes up and brittleness goes up, ductility goes down. Depending on what physical characteristics you want to be present in your steel, that's going to dictate how you heat treat your steel, because as you heat it up, cool it down, you're going to be changing these physical characteristics of the steel. And so, like I said, it's tedious. You need to kind of practice, read into what you're doing, and make sure that you're using the correct heat treatment in order to achieve the physical properties that you want.
Okay, so I have a couple pieces of metal here. This is I'm going to use to show you the temper color, and then we've got a bucket of water that we're going to use for a quench tank. So I have here a little torch with the welding tip on there because I'm going to want to limit my heat input, and I've ground this strip down so that way as the color changes you can get an accurate depiction, versus if we had a piece of steel that still had the mill scale on there. Okay, so I'm going to do this first, show you the tempering colors that it will change, and then I'll move on to this strip, get it nice and hot like glowing orange, and then we'll dip it, and that'll kind of go through all the heat treatments.
that is it. Thank you for watching.